As medical professionals, more so anesthesiologists, we use flow meters on a daily basis, be it to administer oxygen on the ward or administer oxygen air or oxygen nitrous mixtures through the anesthesia machine in the operation theaters. We very conveniently dial up the knob on the flow meter to administer a particular gas either in terms of oxygen or a mixture of gases. Have you ever wondered how exactly these flow meters work? Welcome to this episode of Doodly, wherein we will try to understand the working principle behind this flow meter. Now, before we move on to the function, a brief about the anatomy of the flow meter. For the purpose of discussion, I have chosen this flow meter. If we cut this flow meter into half, vertically down, and open it up, this is what we are going to essentially see. The lower part of the assembly is a needle valve or a pin valve mechanism which regulates the flow, and the glass tube mounted on top is the flow meter assembly, also called as the Thorpe's tube. Now the needle is positioned on a seat of the valve, closing the flow of gases. It's attached by various other components to the knob which is present outside. Upon rotating the knob, the pin moves back from the seat, allowing the gas to flow from either the cylinder or the wall outlet onto the flow meter. Now in the flow meter, we have certain markings which function like a scale and a bobbin which floats up to a particular level to indicate the flow which is happening. How does this bobbin move up or down along the flow meter? In order to understand, let's have a look at the example of Tug of Bar. Here we have a piece of rope which is being pulled by two people. Depending on whoever is stronger, the rope would move towards their side. If both are equally strong, the rope would stay in the middle, not moving to either of the side. Now, instead of having this tug of war which is happening horizontally, if we make it vertical and replace the rope with a bobbin, we will have two forces acting on the bobbin. The one, the gravity, which is acting on the bobbin, trying to pull it down. The other is the force, which is pulling the bobbin up. Now, what is this second force? Now, if you look at the flow meter, the bobbin present in the middle of the flow meter acts like an obstruction to the flow. Thereby, when the flow of gases happen around the bobbin, as indicated by the black arrows, there would be a pressure drop across the bobbin. Thereby, this becomes an extension of the Venturi principle. Before we proceed any further, it is important to clarify and understand a couple of important points. The first one, in this tug of war acting on the bobbin, gravity, which is the downward force, always remains constant. It is only the upward force generated by the pressure drop across the bobbin which varies. As a result, when the upward force is more than the force of gravity, the bobbin would move up, and if it is less than the force of gravity, the bobbin would move downwards. However, if both the forces are exactly equal and opposite, the bobbin would remain at a particular level on the scale, thereby indicating the flow rate happening at that point of time. The next important point is, we know from the Venturi principle that the pressure drop, in this case the upward force which is generated because of that, depends on two important factors. The first is the flow, and the second is the area of the orifice through which the flow is happening. Now we can increase the pressure drop either by increasing the flow or by reducing the area of the orifice. Alternatively, the pressure drop can be decreased by decreasing the flow or increasing the area of the orifice. As an extension of this, when the pressure drop is increasing because of increase in the flow, if we can increase the area of the orifice, we can keep the pressure drop across the bobbin constant, which leads us to the principle of a variable orifice with a fixed pressure drop principle on which these flow meters work. This leads us to the next important principle as to how do we achieve this in the flow meter. So if we look at the flow meter, the walls are not parallel but are slanted. That is, the flow meter is tapered. It is narrow at the bottom and widens as we move up along the flow meter towards the top. So as a result of this, if we take cross sections of the bobbin in the flow meter at two different levels as indicated in the diagram, we find that in the lower part of the flow meter, the area around the bobbin through which the flow can happen is less. And in the cross section which is indicated in the upper part of the flow meter, if we note, the area around the bobbin is significantly more. This gradually increases from bottom as we move up towards the top of the flow meter. This helps in keeping the pressure drop across the bobbin constant. Even as the flow increases as we move from the bottom of the flow meter towards the top. Having understood these three key points, let us start with the flow meter being closed, no flow happening, the bobbin is resting at the bottom of the flow meter. As we slowly start turning the flow meter on, some flow would be registered. Now this flow of gases around the bobbin causes a pressure drop. As the flow increases, this pressure drop progressively increases, and the point where it becomes more than the force of gravity, the bobbin starts moving up. However, because of the tapering nature of the flow meter, as the bobbin moves up, the area around the bobbin through which the flow is happening also increases. This offsets the increase in the pressure drop which happens because of the flow, restoring the pressure drop across the bobbin to a constant amount, which is equal and opposite to the force of gravity acting on it. So when this happens in the flow meter, the bobbin stops at the point on the scale against which we can read the flow rate. Now what happens if we disturb this equilibrium again by increasing the flow? So as the flow increases, the pressure drop across the bobbin increases, thereby increasing the upward force. This causes the bobbin to move up within the flow meter. But as it moves up, the area around the bobbin through which flow is happening also increases, thereby offsetting whatever increase in the pressure drop which has happened because of increased flow. And a new equilibrium with a fixed pressure drop is achieved at a higher level on the flow meter. Similar thing happens when the flow is reduced. If we turn the flow down, the flow which is happening across the bobbin comes down. This results in a reduced pressure drop, as a result of which gravity starts pulling the bobbin downwards. As the bobbin starts moving further down, the area around the bobbin through which the flow is happening comes down. This restores the original pressure drop which happens across the bobbin, as a result of which the bobbin stops at a particular level where both the upward and the downward forces are equal and opposite to each other. Flow meters can be either single taper ones or dual taper ones. Most of the modern anesthesia machines which use a manual flow meter tend to have single taper flow meters, while the dual taper flow meters were usually seen in older anesthesia machines. So, what do we mean by single taper or a dual taper? So, the flow meter on the left side is the classic single taper flow meter, wherein the gradient or the taper is smooth right from the top to bottom. Whereas the flow meter on the right side has got two different degrees of taper. One at the bottom, wherein there is a fine adjustment or fine measurement is possible, and a second taper, which is slightly different on the top, where larger units of measurements are depicted. So the modern machines with manual flow meters have two separate flow meters, one for a fine measurement and a second one for larger units of measurements, both of them being arranged in series. Most of the newer advanced workstations have done away with manual flow meters and they have only a digital flow meters. Of course, they do not work in this way. However, it does make sense to have an understanding about how these flow meters work. The other point which we need to be aware of is the flow characteristics are different at the bottom and the top half of the flow meter. At the bottom, the flow is laminar and the flow characteristics are governed by the viscosity of the gas. While the flow is turbulent at the top, the density of the gas would determine the flow characteristics. Hence, the flow meters are all calibrated for an individual gas and they cannot be interchanged. This brings us to the end of this doodly. Hope you found this useful. Thank you.